So what do you mean by a thread? So as we all know that any application or any program, when we'll execute, so the program under execution is called process. And in the process, there are multiple threads that can be there in a process. So one process can be made of one or more threads. Now you can see that, so in that particular way, we can say that the thread is a basic unit of CPU utilization. So actually, when thread is going to execute into the CPU. So what is a process? Process is program under execution. And you can see the program under execution means there are different instructions in the program, right? So some of the instructions, we can say it is a process which are running right now. And inside the process, we have multiple threads. So you can see that in each process, we have multiple threads. And in each program, we have multiple processes. So a thread is basically a basic unit of CPU utilization. So actually in the CPU, thread is going to execute. So I think you understood the similarity between the program, the process, and the threads, and the differences between all these three things. So as I told you, process is the program under execution, and thread is the basic unit of CPU utilization. It means that thread is going to execute into the CPU. So let's see, what do you mean by a thread? So thread look like a process, okay, but it has its own ID. Like a process has the process ID. Here, thread has the thread ID. So there is a thread ID. There is a program counter also in the thread. Like in the process, we have program counter. So in a process, there are a number of instructions. So which instruction will go to next, or which instruction will execute next, program counters decide. In the same way, in thread also, because thread is the smallest unit a CPU will utilize. So thread is also, there are some set of instructions. So which instruction will go and execute next will be taken care by the program counter. There is a register set. So I told you the usage of register and stack, and when we learn about the process, that the register will use to have different values related to the programs, and the stack will have the recursive functions and the functions call, and all those things will be taken care by that stack. So all those things are there. Means we have thread in a process. In a thread, we have thread ID. We have a program counter, and then we have a set of registers, and we have a stack. Okay, so all those things are there separately with each thread, as well as thread shares. What it will share? It will share with other threads belongs to the same process its code section. So what it is going to share with other threads? It is going to share the code section. It will share the data section and other operating system resources such as open files and signals. So all these three, four things it will share with other threads also. And other threads, which other thread? The thread belongs to the same process. So you remember that the program is nothing but, the process is nothing but program under execution. So you can see that one program or one application has many processes. One processes may have many threads. Okay, so it is like that only. So there is a mapping between all those things. Now, if I'll say a process has all those things, right? It has its code section, its data section, its stack, its register, its program counter, its ID, its open file, its open signals. So all those things are there. But if we create a thread out of a process, or when we create multiple thread out of a process, so these things should be common. So these are the common thing, that is the code section, data section, open file, and signals are same for all the threads, belongs to the same process, and all those things are separate to the thread itself. When we talk about a traditional or heavyweight process, it has a single thread of control. So if we'll talk about heavyweight process, or if we'll talk about traditional process, it has only single thread. So one thread is there, and that thread is going to execute into the program. But there is no multiple threads in a process when we talk about traditional or the heavyweight process. If a process has multiple thread of control, it can perform more than one task at a time. Definitely, if a process has multiple threads, so with the help of multiple thread, it can perform more than one task at a particular time. With the help of parallelism, it can achieve it. Let's see with the diagram, and we understand that what do you mean by a traditional heavyweight process which has only single thread, and what do you mean by a process which will have multiple threads. Okay, so this is the diagram which will tell you that we have a single threaded process. It is also called heavyweight process or a traditional process, in which we have only single thread. So we have only single thread belongs to that particular process. And here you can see there is a code section, data section, open files and close files. Then we have different signals, register and stacks. All those things belongs to one process only. And because that process is having only one thread, so you can say all those things belongs to one thread only. But when we talk about multi-threaded processes, where we have multiple threads available. So in this particular example, you can see that what are the common thing? We have the code section, we have the data section, which is, and the file and the signals are common between all the threads, but there are separate register and the stacks which are separate. There are separate program counter and there are separate ID. So all these threads are having IDs. So let's say the ID is 1, 2, 3, and there are some program counter also, which is dedicated to these threads only. So you can see that that's why the thread is called lightweight process. Okay. So in a multi-threaded process architecture, the threads share the code, data, and file section, and they have their own local register, stacks, program counter, and they all have their own thread ID. That's why in a multi-threaded process architecture, the threads are called lightweight process. So that thread that belongs here in a multi-threaded process, we can say it is a lightweight process. Okay, and this thread is nothing but heavyweight process. This is called heavyweight. Okay, so you understood it. This is a heavyweight, or you can say a traditional process. This is a lightweight. That thread, only that thread we can say it is a lightweight process. Okay, so I think you understood the difference between a traditional or heavyweight process and multi-threaded process architecture. So in a multi-threaded process architecture, we have multiple processes. All those multiple processes have their local ID, their program counter, their stack, their registers, and they used to share codes section, data section, close and open file list, as well as different signals which belongs to the process. Let's see one example. So this one is a thread viewer application that we can install in Windows operating system. And you see when you open that particular application, which is called thread view, On that you can see different processes that are running right now. So let's say there is a Chrome we have opened, and Chrome belongs to, and we have created different instance of the Chrome. So there are different processes that has been created. So we have only one program, which is a Chrome program, but we have multiple processes. So you can see that these are all different processes, and these are the process ID given to it. So there is one program, there is a Chrome. You can see it is okay. So let's assume that we have a program, and that program has multiple processes, and one process has multiple threads. Okay. So let's say we have a program called Chrome. That one program is creating multiple process. So here you can say different process IDs are there. So we have multiple instance of Chrome. Let's say in one Chrome tab we have opened one website, another Chrome we have opened another website, another. So in that way, let's say we have in one Chrome we have open a mail, and in that application only we have open application called, let's say, create mail. So when we click create mail, another thread will be coming up from one process. So that is, there are, for one instance of a process we have multiple threads, right? And you can see that if we have only one tab, let's say we are downloading the file from the mail, that downloading will creating another thread. So that's why you can view your mail at the same time you can download a file. So you can see that one processes may create multiple threads. Let's say we'll click any of the process. So once we click any of the process, it will go and open the process. So that is a process threads view application, in which we can see the thread ID of one process. So that is a thread ID of one process. Okay, so you can see that multiple process. If we'll click any of the process, it will go here, and you can see that there are multiple threads. You can see here multiple thread having their ID, how many times they have done the context switching. Do you know the context switching meaning? The meaning of context switching is when we are allocating the CPU and when we are deallocating the CPU. So in between, there is a switching that will take place. Means the process control block of a process, or here it is thread, will be saved, and another process control block of a new thread will be activated and will be loaded into the different registers of the CPU. That particular is called, the process is called context switching. Okay. So when we do context switching, so you can see that how many times context switching has been taken place. So here this particular thread has 3 context switching, 2, and this particular thread has many context switching. Here also we have many context switching. Last context switching is status, so it will tell you that how many times they have or when they have done the last context switching. And the status, there is a user request, there is a WRQ, there is a user is WRQ. So these are different status. Let's go into detail again. So when you see that, so we have a thread ID, we have the context switches, the last context switches, the status of it, and then you can see here created time. So when these threads are created, so it depends upon your click, right? So when you click a hyperlink, it will create another tab of it, or another threads from that same process will be created. Here you can see the user time, the kernel time. So this is telling you the time, the visible, hidden, and then if you'll go again, so you can find it here, the start, the address of that particular threads in the main memory. Then there is a stake. I told you there is a separate stack and separate register, right? What else they have? They have program counter and they have their thread ID. So thread ID is there, program counter is there, stack is there, and registers are there. So about the stack, it is telling you the base address of the stack, the limit of the stack, and the size of the stack. So in that way, they have the stack detail also. Right. So this particular example will tell you that how when we go for creating when we go for running a program, it will create multiple processes, and one processes may create multiple threads, and you can see what is inside a thread. So we have its ID, we have its program counter, which is not listed here, but you can see the stack and all. So this is how your thread look like. Okay, now once we have seen what do you mean by thread, what do you mean by the heavyweight process, and what do you mean by lightweight process, let's see and find it out some of the benefits related to this threads. Okay, so there are generally four benefits that we find out related to multiple threads of a program or a multi-threaded programming architecture. So the first benefit that we find out is responsiveness. The meaning of responsiveness is, let's say when we do a scheduling and we have a process, when we say it is a, what is a response time, so we say the response time is when a process get the CPU. So at that particular time we say it is a response time. So here also is the same. Responsiveness means whenever a process is created, or whenever we want to run a particular task, or when we want to run our particular program, that program should be open as soon as possible. That is our requirement, right? So when I open the Chrome application, it should open as soon as possible. So how it will be possible? It will be possible in a responsive operating system. So when my operating system is responsive and it is giving me a response as soon as possible, then only it is possible. And it is only possible with the architecture of multi-threaded architecture, where one process will create multiple threads, and one of the thread will get the CPU, because we have multiple thread belongs to a process. So one thread will, when it will execute into the CPU, we say it is a interactive operating system. So responsiveness is the first benefit that we got when we use multi-threaded multi-threaded programming architecture. Now, in a multi-threaded and interactive application may allow a program to continue running even if a part of it is blocked or is performing a lengthy operation, thereby increasing the responsiveness of the user. So what it want to say is, let's say if we are using a heavyweight process architecture, in which let's say we have opened a Word file, and after that we want to open Chrome. So Word file, because it is a heavyweight process, it will execute and it will take a lot of time for context switching and all. And then we have to put the heavyweight Chrome onto it. So it will again take a lot of time for the context switching and all. So to reduce that, if we'll use multiple threads, the switching between the threads will be very easy because it is a lightweight process, and they doesn't have a much thing in a separate. So we are in the benefit of multi-threading operating system. So as I told you, because threads are of lightweight, so to context switch between threads are much cheaper than the context switching between the heavyweight processes. And it will now what it will do is it will uh, increase the time when we have multiple processes, when we use multiple heavy processes, so responsiveness may decrease. Here it also says that when we use the multi-threaded architecture, so what will happen in a multi-threaded architecture, it will create an interactive application. It may allow a program to continue running even if the part of it may be blocked. So let's say if one process is there, and that particular process has multiple threads, and let's say one thread will become blocked. So we have many other thread which can run. So you can see it will make my process interactive, and when one thread will be blocked by some system call or some other thing, or maybe that cannot make sure that it will become a parallel. So we have some more threads also which can run, and ultimately the process is running, and ultimately we say that that program is running. Getting it? So that's why it make the system more responsive. Next is the resource sharing. It has the architecture that the thread share resources and memory resources. So it will share the resources, and there is memory resources, the processes to which they belongs to. So they share the memory, and they share different type of resources also. So they share the resources and they share the memory uh, with with the process which they belongs to. So definitely, if we have threads, and if I'll say that there is a thread 1, and there is a thread 2, and there is a thread 3, and all these three threads are sharing some resources. So we can say that that particular resource belongs to one process only. And if I'll say that, then we can say that all these three threads belongs to that process only. So multiple threads may be created from the process, and these multiple threads share their resources and memory belongs to the same process. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. So it says that within the same address space, it can allow an application to have several different threads. So because of sharing property, we can have multiple threads, and for creating all those multiple thread, we doesn't have to do allocate much resources, because we doesn't have to allocate the resources to all those threads separately, because they are using the memory, they are using the codes, they are using the data, they are using their open and close files. So in that way, with one address space of the memory could be used by different threads, and that is a property of resource sharing. So it can share the resources. Next is economy. It is economically more cheaper. How it is cheaper? So cheaper than the process creation. So when we create a process and when we create a thread, which one is cheaper? The cheaper is the thread creation. Why? What is the reason? The reason is because when we create a thread, we doesn't have to create the whole memory address space for that, for one thread. Actually, we are sharing the address space with all the threads. So the thread creation is not costly. Thread switching lower overhead, as well as to switching, context switching also will be having lower overhead. Overhead will be less. Why? Because when we talk about responsiveness, at that particular time we have seen that when we have a heavyweight process and when we want to switch between two heavyweight process, so to store their process control block of those two heavyweight process, it will take a lot of time. While because most of the things are shared between the threads, so as well as these are all lightweight processes, so the overhead will become uh, less, very less. Allocating memory and resources for the process creation is costly because when we talk about process, so the memory will be created, so resources will be allocated. But here memory and resources are shared. That's why, so because the thread share resources of the process to which they belong, it is more economical to create and context switch thread. So for creating a thread as well as for context switching, it is more economical. So that is the third advantage of multi-threaded programming architecture. The last benefit will be scalable or utilization of multi-processor architecture. So when we talk about today's generation system, we have i3, i5, i7, right? And I don't know whether i9 is available or not. Maybe i9 will be available for some period of time, but let's say these are the variation in the personal computer. We have servers, uh, we have mainframe, we have uh, HPC, high performance computing system. So here also we have multiple process, right? So we have let's say we have octa process, or we have some process with hyper threading concept, or we have some process, let's say we have 10 number of cores or that much of. So if we have one processor and multiple cores are there, it means that it is a multi-processor architecture. We have multiple processors. And when we talk about high performance computing, so we have, let's say, 64 number of processors, and each processor will have, let's say, 16 core, right? And we have, let's say, 16 number of GPUs, and each GPU we have multiple cores, let's say 16 number of. So you can see that these much of computing power we have. So how we can actually utilize them, right? So when we utilize them using the multi-threaded programming. So when we are running one program and when we have only one thread architecture, it will take a lot of time for processing that particular program or to executing that particular program. But when we talk about multi-threaded programming architecture, we can achieve parallelism, and one process which have multiple threads, and all those threads are independent to each other, all those threads can be executing at the same time. So that concept is called parallelism, and parallelism is possible when all the threads output will not affect other threads input. So it means that all the are independent to each other. So in that way, parallelism will be achieved, and all the thread can execute at the same time, and we can utilize these. Let's say we have how many threads? 1, 2, 3, 4, 5 threads are there. And if we have, let's say, octa-core architecture, where we have 8 cores in a CPU, so we can allocate one core to one thread to one CPU, and in parallel processing we can execute it, and we can utilize that multi processing architecture, and we can increase the scalability. Means multiple processes. So this is one process. So we have n number of process can be run in this particular architecture, because one processes will have multiple thread, another processes we have multiple threads, another processes we have multiple threads, and all those threads could be run parallelly. Means some of the thread could be run parallelly, right? And most of the process could be run concurrently. So there is a process of parallelism and there is a process of concurrency. Concurrency means multiple processes can run at the same time, and parallelism means multiple thread belongs to the same process can run at the same time. So the benefit of multi-threading can be greatly increased in multiprocessor architecture. So it means multi-threading and multiprocessor are complementing to each other, where threads may be running in parallel, right? So parallelism will be achieved. Different processes. A single thread process can only be run in the CPU, no matter how many are available. So it says that only single thread will be running in a process. So one process or one processor. So one processor or one CPU will take one thread. It means that if we have multiple process or if we have multiple cores, so we can provide multiple threads to them. Multi-threading on a multi-CPU machine may increase the concurrency. So parallelism and the concurrency could be achieved. So parallelism would be achieved with multiple threads which belongs to the same process, but those threads should be independent, right? And concurrency means multiple processes will be running. So multi-programming or multitasking operating system would be achieved through concurrency. Means multiple CPU could be utilized. So these are different benefits related to the process itself. This is a multi-threaded server architecture in which, let's say we have a client, it is requesting something. We have a server. So what server will do is it will create a new thread to the service request. Thread will be created and thread is serving that particular request. And what it will do is resume listening the additional client request. So whenever we have another client request, another thread will be created. It is like this. Let's say we have a server of Gmail, and let's say there is a user one requested for its mail. So what this server will do, server will create a thread which belongs to the user one, and the thread will serve the user. Its request will be served by the thread that will be created by the Gmail server. Another user, if it is interacting with the Gmail server and requesting for something, so it will create another thread which belongs to user 2, and this will serve the user 2. So you can see that in a multi-threaded server architecture, it will work like that. And that's why if I'll open the Gmail account, it will be open for in a fraction of second. So you have to know that when I am opening a Gmail account, at the same time, millions of people are opening and giving a request to Gmail to open their Gmail account, right? But it will serve to all the users. So how it is possible? Because it knows that for opening a Gmail account and giving a window of, let's say it's putting its username and the password, means for the credential page, there is one process. So it will create multiple thread of that particular process, which is nothing but creating a or giving the window for username and password, and it will create different threads, and one thread belongs to one request. So one request will be fulfilled, then thread is executing, and it will terminate. And then in terms of another request, it will create another thread. So this is how your multi-threaded server architecture actually works. Let's talk about multi-core programming. So multi-core programming, it means that we have just seen that if we have multiple processors available in the system, or multi-core available in the system, then how this multi-threading concept will be giving us the benefit. So it is giving us the benefit of parallelism, and it is giving us the benefit of concurrency. So let's talk about parallelism here. When we talk about parallelism, we have two types of parallelism: the data parallelism and the task parallelism. What is the meaning of data parallelism? So it will distribute subsets of the same data across multiple core, same operation on each. So what will happen is in a data parallelism, let's say we have different datas, and all those if we have one data, and we'll create the copy of that particular data, and we'll distribute all those data to multiple core. Second, we have the task parallelism. Task means there is some functions, right? So distribute thread across core, each thread performing some unique operation. So we will give the different task, and we'll say that when we run the task, it is not going to affect another task. So in that way, it will be creating the parallelism. Okay. So it says that distribute subset of the same data across multiple core. Here it says that distribute threads across cores, each thread performing the unique operation here. So when we distribute the thread, it is called task parallelism. And when we distribute subset of the data across multiple core, it is called data parallelism. So multiple thread will achieve the task parallelism. As number of thread grows, so does architecture support for thread. CPU have cores as well as hardware threads, and consider Oracle Sparks T4 with 8 core, 8 hardware thread per core. So it is some sort of the processor which has 8 core and 8 hardware thread per core. So you can see if we have one processor available, and each processor has 8. So if we have 3, 4, 5, 6, and we have 7, 8. Let's say we have 8 cores available, and in each core we have 8 hardware threads per core. So we have, you can see, 8 which belongs to. So you can see this is one processor. We have 8 cores, and in each core we have 8 hardware thread we can have in per core. So 8 thread could be run parallelly in one core. So how many threads could be accommodated here? So 8 into 8, 64 threads could be run parallelly in this particular architecture of a processor. So you can see that these type of CPU is also available with us, which can run multiple threads, and it can achieve parallelism. Which parallelism? Task parallelism. So when we distribute the threads across cores, that is called task parallelism. Or when we distribute subset of same data across multiple core, that is called data parallelism. So data parallelism is different, task parallelism is different. But with the help of multi-threaded operating system, or sorry, multi-threaded system, we can achieve task parallelism. Now let's see the difference between concurrency and parallelism. Parallelism, the concurrency means if we have multiple tasks, so when we accommodate multiple tasks to run in a single core, that property is called concurrency. It is like this. Let's say we have a database. Let's say we have PVR. Okay. PVR. Let's say in a Bhubaneswar, we have one PVR. We want to book the ticket. So let's say we have multiple users which are interacting with this particular database. This is user 1, user 2, user 3, user 4, user 5. And all those different users want to book the seat in the PVR. So what will happen is we'll allow all the user to book the seat in the PVR at the same time. It is possible when all the user are going to book the different seat. When they want to book the same seat, so the concurrency could not be achieved. It will become serial. Okay. So concurrency achieve non-serial scheduling. As the when it is possible, when we doesn't have shared resource. Now here, if we'll talk about the shared resource, which is of single core, so how we can achieve concurrency in a single core? So we have to give time slice like a round robin. We have seen round robin, right? So we'll give the time slice, let's say 2 milliseconds to one particular task. So we'll give 2 milliseconds to one task, again 2 milliseconds to another task, and again 2 milliseconds to another task, and again 2 milliseconds to another task. We have only 4 tasks, let's say, in our system. Then again, T1 will get the chance, T2, T3, T4. Then again, T1 will get the chance, T3. In that way, it is going to execute in a single core processor where we can achieve concurrency. So concurrently, we are allowing all the process to run into the CPU one by one. Now, if we'll talk about parallelism, parallelism could be achieved with a multiple core process where we can have at the same time T1 could run, at the same time T2 can run in a round robin fashion. Then again T3 can run and T4 can run. Again T1 can run, T2 can run. Again T3 can run, T4 can run. In that way you can achieve parallelism. That is called parallelism, and that is called concurrency. So here we have only one resource, that is PVR, and we are allowing multiple users to book the ticket into one database. It is just like a concurrency. And when we want to achieve parallelism, it means that we have multiple cores available, and we are allowing and we are dividing the task into 2 parts, and one set of tasks will provide to one core, another set of tasks will provide to another core. So at the same time, both the task is completing its execution. That is called parallelism. Parallelly, if we are executing all our and we are utilizing all our cores. Let's talk about different types of threads. So we have generally 2 types of thread. One is called user thread, another is called kernel thread. So user thread, it will be managed by the user level and it is created by the user only. Kernel thread, it is actually managed by the operating system, and it is also created by the operating system, right? Just like different type of system call. Okay, and looking for looking for handling interrupts, right? So at that time, it will be kernel thread, and user thread is created by the user program or the process which is running by the user. So we have different libraries, like in POSIX pthread. It is in Unix operating system will generally see that. Windows threads are there, Java threads are there, different type of threads are there. We'll see all those things later on. Then we have kernel threads, different system calls, which is creating it. Virtually all general purpose operating system, including Windows, Solaris, Linux, Turn 64, Unix, Mac OS, all those OS has kernel threads. Okay. Let's see the difference between these two threads. There are the relation between all these threads. Those are many-to-one relation, one-to-one relation, and many-to-many relation. Let's see all those relations one by one. Now let's talk about many-to-one relation. In this particular architecture, what will happen is we have multiple threads, and all these multiple threads belongs to only one kernel thread. So all those multiple threads belongs to one kernel thread. That type of architecture is called many to one architecture. So what happened in many to one? Many user level threads map to a single kernel threads. So one thread blocking cause all the blocks. So what will happen is, let's say one thread is calling a system call for block. So what will happen is, because each thread belongs to the kernel thread, because it is a system call, so definitely kernel thread is going to execute it. And once the kernel is going to execute it, it will block. So it will block itself. So all the three which is not calling the block will be blocked automatically, because all those are belongs to the same kernel. It cannot execute further. So the execution of these threads are not at all possible. So multiple thread may not run in parallel on multi-core system, because only one may be in kernel at a time. So what it want to say is, this is one problem. It says that if one is saying the block, then the whole process will be blocked and no one can execute. Second, parallelism is not at all possible. Why? Because if these threads are independent, but these thread belongs to only one kernel, so one kernel is going to execute. And if only one kernel is going to execute, how the parallelism would be achieved? So that's why the parallelism could not be achieved. Few systems concurrently use this model. So we have Solaris green thread, or we have JNU portable threads. These two are the example which uses many to one relation between the user thread and the kernel thread. Okay, so yes, so that's why this even though we have multiple thread, but we cannot achieve parallelism. So parallelism is not at all possible. Second thing, we cannot achieve multitasking is also very difficult. Okay, multi-programming is also very difficult in these type of architecture. So we have another type of architecture which is called one-to-one. Each thread belongs to a separate kernel. So if, let's say, one kernel is calling the block request or the block system call, so only one kernel will be blocked, but the other kernel would be running. And in that way we can achieve parallelism, as well as we can achieve multi tasking here. So each user level thread map to kernel thread. Creating a user level thread creates the kernel thread. So whenever we are creating a user level thread, we have to create a kernel thread which belongs to that user thread. More concurrently could be concurrency could be achieved here. So concurrency, more parallelism should be achieved here. It says that, and number of thread per process sometimes restricts due to overhead. But what is the problem here is, if you are creating multiple user thread, and because if we have created m number of user thread, we have to create m number of kernel thread, which will make our system heavy, and which will unnecessarily create which will unnecessarily full the main memory, and that way my system could be slow because of the heavy deployment of the user thread as well as kernel thread. Because if we have, let's say, 100 number of user thread, we should have 100 number of kernel thread. So it may increase the cost and decrease the performance of the system. Number of thread per process sometime restrict due to the overhead. So that is the overhead that has been created. Next is many to many. In that, what will happen is, we have multiple threads, and that multiple thread may belongs to multiple kernel. So we have m number of threads that we are creating, and we are having n number of kernels. So it is a m to m, or you can say many to many, but here m should be greater than n, greater than or equal to n. This is the relationship between them. Means user threads are more and kernel thread may be same, equal, or less. So it says that allow multiple user thread to be mapped to the many kernel thread. Allow the operating system to create a sufficient number of kernel threads. So it can create sufficient number of kernel thread. It doesn't have to create, let's say if we have 100 user thread, so it doesn't have to create 100 user thread. It may create 50 user thread, right? So even if one is blocked, it can block only one. So 99 is running, and here 49 will be there. So there is no problem on that. A concurrency would be achieved. Parallelism also could be achieved. That is the architecture that many operating system nowadays follows. That is to many model, where we can achieve concurrency as well as parallelism. And it will be, you can see, it will be it will not make our system costly, or it will not create any sort of overhead.